Thank you very much, Marco. Yes, to explore galaxy, what's the best to start with our planet? Indeed, it's a beautiful, colorful planet. When I get asked, what is your favorite planet? Planet Earth, there is no doubt. Look at the colors and the variety. Because in reality, the space is desperately dark and also empty. In fact, the density of matter in general is 1 atom of hydrogen per cubic centimeter, which is very, very little. On the other hand, if you stare long enough to the dark sky, and this is the very famous deep field of the James Webb Space Telescope, there was a back in 96, the first deep field of the HST. Maybe the redshift is comparable, but look at the detail that James Webb can actually offer to us, and not only in terms of galaxies, but in terms of these Einstein rings that testify actually the general relativity works on the larger scale. So from this darkness, if we stare long enough and we collect enough photons, we see actually a multitude of galaxies, and that's the actual light of the universe. There are other things that are very interesting in the universe, but they don't give us the light, and as I will show you, they also don't give us a time scale to time the evolution of the universe. So as Marco alluded, this talk will be describing how are we basically able to model the light that we see and translate it into physics and astrophysics, but also the darkness of galaxies in the cosmos. Starting with our home, the Milky Way, that I thought last week there were unusually clear skies in Portsmouth. I really love it. I could see a lot of details, but this, of course, comes from the southern hemisphere. And that's what you see is part of the arms of the Milky Way. Let's describe, for those of you that are not expert of galaxies, if any, otherwise this is a repetition of what a galaxy is in general. Is in general a virialized system, is a big system containing components that are stars, more or less settled in coherent structures that we will see. This is just a spirals. There is a central region, a planar distribution of stars and gas that actually subtend rotation, and everything is embedded in a container that would be dark even without speaking of dark matter, where we'll come back to this. And embedded in the very center, we call it the nucleus of galaxies, which in most cases in the local universe doesn't do very much, but in reality, especially back in times, is the place where supermassive black holes in galaxies are located. So these components actually tells us about the cosmic history of structures in the universe. Stars are crucial not only because they give us the illumination, and we will learn how to model, but they are also the sites to create a chemical element. We know that Big Bang nucleosynthesis give us hydrogen and helium and just traces of other things, of light elements. However, all the rest come from stars. We have gas and dust that are the fuel for star formation, and these beautiful fingers, this is a James Webb Space Telescope image, and if you compare this, the detail that you can see here with what the HST showed us, it's just astonishing. We have black holes, not in all galaxies, which is an interesting problem, and also we have got dark matter, which it has been around for many years, for many decades. We're still missing exactly to say what it is. We'll come back to that. But especially what I wanted to say, galaxies come in reality in various, let's say, morphologies, you would say, shapes, structures, and that got the name, the Galaxy Zoo, a name that was actually cognated in Oxford when I was there, by Chris Linto to actually then pursue this project. What does this mean? That there are many galaxies. And we certainly don't want to entail the exercise of trying to understand one of each. We need to categorize them and to try to grasp their formation mechanism. The main types are certainly ellipticals, spirals, dwarf that you see on that side, where you see stars distributed on a relatively large area, but the amount of light from the dwarf is very small. And then there are transitioning stages that we call mergers, where galaxies get together. Galaxies are not only very many in space, but also in time, and we don't couple these variables any longer since the relativity of Einstein. And if you look at the biography of the universe from the Big Bang to our local time, well, galaxies appear very early. And actually, the last 2 years of the James Webb Space Telescope have actually showed us they may even appear earlier than the cosmology thought, which is a very interesting problem. After a period of dark ages, the hypothesis is you first need to form the first stars, and those stars then will give origin by getting together to the first galaxies. And all this period, for which we don't know very much yet, is what is probed by the James Webb Space Telescope. At some point in the late time universe, our sun gets to be formed with 2% chemical composition. So it takes like 10 billion years to evolve from 0 metals to 2%, which is an interesting problem, and the planet with it. I just want to drop another information. The birth of the sun coincides with the epoch at which astronomers have discovered that the universe is expanding in acceleration. There are many cosmic coincidences that you get to know if you are a professional astronomer, but this is quite interesting to me. So roughly redshift 0.4 or 4.5 billion years in the past. Now, let's first speak about the light that this galaxy gives us, because obviously we are professional astrophysicists. It's not very, we don't get much by just looking at galaxies and finding them pretty. We need to get out the astrophysics. Obviously, the light of galaxies will originate from the number of stars that constitute galaxies. There can be thousands, billions of stars. They can be like the sun, they can be different from the sun, but that's for sure. So, first of all, if you take the energy of a galaxy with instrument and you look at it as a function of wavelengths, what do you see? This is the spectrum of light of a massive galaxy. I say massive in the sense that this is about 10 to the 11, the mass of the sun. This is from the Sloan Digital Sky Survey that has collected the largest number of spectra of galaxies in the local universe, that we are full members in Portsmouth. But I just wanted to show you the beauty of this, and especially the lines that you see, carbon, nitrogen, calcium, iron. Let's see whether we say, so calcium is up there, give us quite some lines. Iron, obviously, with so many electrons, is distributed everywhere in the spectrum. Magnesium, which turned out to be a fundamental tracer of the formation epoch of galaxy. We showed that back in 2005. I don't have the time to explain why, but it's a strong line that is also needed to locate the galaxies at a certain distance. Sodium is a very important element that actually astrophysicists studies over the past few years, because it could tell us about the early formation epoch of this galaxy. So essentially, this is what the observation gives you, and you would like to find theoretical model for this. Okay, so here is what we see, and now I tell you what we can do from the modeling side. First of all, where does the energy of stars come from? If you are an undergrad student, certainly someone has proposed to you that the energy, the equation of Einstein, E equal mc squared, is actually what's happening in the core of stars, with some appropriate coefficient that are related to the specific type of burning, but at the end of the day, stars are converting matter into energy following this equation. So the star, any star, this is beautiful. I actually don't remember if this is the sun. It could well be the sun. Some visualization. Is a giant balloon of gas that remain composed by 70% of hydrogen, 28% of helium in case of the sun, and just 2% of heavier element. And it's amusing to think that just those 2% allowed us to actually determine with an excellent accuracy the age, the formation epoch, the chemical composition of galaxies as near the Big Bang. If we take a walk into the sun, it's important to see where actually this energy comes from, because it's all what I'm saying is very local. Our star is there, but what I want to have and obtain is a model that applies to the most distant. So stars actually burn part of their core, the inner core, where temperature and density are high enough that actually nuclear fusion can start. And if they are not high enough, we speak about failed stars, brown dwarf, or planets. So inside the core, there is this giant site of burning of nuclear fusion. Now, in any arbitrary galaxy, however, we know that not all stars are like the sun. In particular, we distinguish stars in two main categories. Low mass stars, that are actually by far the most numerous in the universe, that evolve up there, they live, Arthur Eddington has shown actually, and not only him, of the order 10 billion years, like the sun. They then expand into red giant, lose their envelope, become a planetary nebula, which is a transient phase, very beautiful, but especially evolve and decay, become a white dwarf, which is a very hot sphere of inert material. That's low mass stars. But the stars that are much more massive, that we call high mass stars, evolve according to that branch. Their typical timescale of evolution is instead of the order 10 million years. So very quick. If you remember when the dinosaurs were on Earth, is 65 million years ago, massive stars live much shorter. But what they do, first of all, they are very luminous. And also, they fill the universe with their remnants, which are black holes and neutron stars. And in virtue of their giant envelopes, they actually produce a lot of chemical elements and distribute it around galaxies. So, in principle, to calculate the total energy emission of any arbitrary galaxy, you immediately can conclude that you have to find a way to integrate over the total emission of all the stars that are in that galaxy. A work that you can only do theoretically because stars can be resolved from Earth only in the Milky Way and in a few galaxies around us. But when you go far away at cosmological distance, a galaxy appears just a blob of light in the sky. So, this is a problem that astronomers started to think about in the 70s. How can we calculate and predict the energy emission of an entire galaxy? And that's a problem that is called population synthesis. One of my daughters studies psychology, and population synthesis is also a naming that you use there for completely different reasons. But presume you have a population of humans with a spread in age, a spread in other things, and you are in a community like this room, and we can look at each other in our face and we know all the details. Then you zoom out, you get into a crowd, and what you distinguish there, you don't get the detail at all, but you actually have a sort of sense of how many of these people are there. If you zoom out further, you actually will conclude what are the most luminous members of this picture that happen to be actually the UK, Italy, and the Netherlands, probably. And all the rest is less contributing. That's the problem of trying to integrate a population okay, from the distance. It's an analogy that I use to explain how we do population synthesis for distant galaxies. This graph shows the stellar field in the Milky Way, and this is an HST image. It shows bright stars and dots that I will tell you later what they are. Some of you may know it already. So we are relatively proximate, and we can actually say this star is yellow, the other is green. If we zoom out, we notice that stars actually clusters. This is a cluster of stars. About 1 million of solar masses make this cluster. Here, you would say that the cluster is very dense in star, but you don't distinguish much. The members, and then if you zoom out, that you have the whole galaxy. There will be no way that you can resolve every individual star in the galaxy. We don't want that because we have theoretical understanding of how stars evolve. So we want to make a global model. And especially in this day, I'm very pleased to give tribute to the foundations of this theory to Beatrice Tinsley, a British-born astrophysicist who worked at Yale, who actually made the foundation of the models that I actually, on which I work, that is called evolutionary population synthesis. Evolutionary means that you want to take into explicit account a theory called the stellar evolution that would tell you, without you seeing the stars, how much light you get out from a 15 solar mass stars, how much you get from other smaller members as a function of mass. And in a nice statement that she wrote in a paper together with my PhD supervisor back in 1981, the contribution from these different stars to the light of a galaxy is proportional to the energy of those stars, which goes as the Einstein equation, but also to the lifetime. As I told you earlier, very massive stars live very quickly. So they give us a lot of light, but not for a long time. On the other hand, low mass stars lives the whole of the Hubble times, giving us a bit of light, but not comparable. So in reality, when you do this type of model, you have two main parameters, the energy and the time scale. Now, just for your eyes, I want to show you how the individual stars shine. These are spectra taken in a collaboration that includes us in Portsmouth, that is the largest collection of stellar spectra, 60,000 spectra indeed, taken with a telescope that is proprietary, the Sloan telescope. And what you see here is something that you may be familiar. You see the emission of light as a function of wavelengths for more or less the optical near-infrared. Hot stars are up there. They give us a lot of energy at the shorter wavelengths, and they have distribution that are very smooth. Cold stars, of course, their peak shifted to longer wavelengths. This is a physics law that is called the Wien law that you study at your second year of physics, where the energy emission is related to the temperature and the wavelength. It's called the Wien law, and astrophysics absolutely fulfill that. But also, you see a lot of molecules. I show these individual spectra, because if you remember the galaxy spectra I showed you earlier, that is the result of the integration of all of this with different weights. So, speaking generally, the components of models like the one that I calculate will include to estimate the energetic of each of your stars that you think they are in your far, far away galaxy, how long they shine, so the time scale, and then the basic question, their distribution. In this room, we have roughly 50-50 girls and men, I don't know. I'm just making a rough estimate, okay? Maybe not. How do you know how many high mass stars or low mass stars are in your galaxy? Believe me, this is one of the central problems in astrophysics. It's called the initial mass function. Does not yet come from theory. And we have just estimates of this function in the Milky Way that other people made. Okay? It's a theoretical function. You can write it down with an equation, but the thing is that we cannot predict it. So you assume a distribution that will tell you how many small mass stars, how many intermediate mass, and how many high mass stars. Why you want to do that? Because they have different energetics and different timescales. And after you do this, you do a nice integration, and I apologize for the fonts, with the weights, and then you give this to a supercomputer. This is our supercomputer, Shama. This picture is a bit obsolete. We have many more cores. Marco told me that you have a supercomputer also here. And the outcome is this one. What I'm showing you are now not observation, rather theoretical spectra of arbitrary generation of stars spanning a wide age range from 1 million year to 10 billion year. So I'm looking at very young stellar generation and how they change with time. And when I give this type of talk, I say, well, stars and like people, we age, unfortunately. So the way stars age, they change the peak of their energy distribution, stellar population. So up there, that side, with a lot of ultraviolet light, corresponds to very young stellar generations, so young models. And on the other side, to older populations. Why is that? Because massive stars live very shortly, they are very hot, they emit in the ultraviolet, and because they live shortly, only young population will have them in abundance. And that's why the spectrum of galaxy, as we think, will change following the death rate of their stars. Now, these models is what Marco alluded. You need this model to make sense of the observations. Now I'm showing you, many people do this in the world, and we are one of the schools doing these things. How do you compare your models to data? This is a physics approach. You take an estimator of the goodness of your matching, which is usually the distance between your model and your data, I-square. I hope it rings a bell. Or you define any other distance. Obviously, your best fitting model is the one that gets closest to the data. And I'm showing here one example of that, where this valuable early career researcher, Justus Neumann, has actually processed of the order of 1.3 now in a million galaxies from the Sloan Digital Sky Survey and make everything available. What do we mean by process? We match this data, which are the data are the black, with models in a large family, because you don't know how galaxies evolve, so you want to give them all the possibility. You use a nice code, minimize, and find the best fitting. And for example, for this very galaxy that I'm showing here, we could say this galaxy is about 4 billion years old, so it formed 4 billion years in the past. D over H is a coordinate that tells you how chemically enriched it is with respect to the sun. This number being 0 refers to the sun. For this galaxy, we have 0.2, meaning this galaxy has even more matter than the sun. And finally, M star is the total mass in stars of this galaxy. And in this case, it's 1.5 in 10 to the 8, the mass of the sun. And you do this for all the galaxies that you can, and this is what astrophysicists do. Stellar population models or stellar evolution is the only way you can age date galaxies. There are no other way. Essentially, what we do, we exploit the known timescale of nuclear fusion, age date the most distant galaxies. And this is really, if you think about, an incredible theoretical jump, and it works very well. So for the light, we can come back to that. But in reality, And I couldn't find a black square, so I used a blue square. But in reality, is there darkness in galaxies? Actually, yes, of two kinds. Not only galaxies are embedded in the dark space, but there is darkness in them. What is it? As people, stars live and die. And I told you earlier that. But that means that at any cosmic epoch, a galaxy will be composed by living and dead stars. What are the dead stars? The type of remnants that I mentioned earlier, white dwarf, neutron stars, and black holes, mini-stellar black holes. The dead stars do not shine, but they give you a lot of mass, and they hang around in your galaxy. Okay? In reality, in the 70s, that stellar remnants, so the dead part of the stars, were thought to be a highly promising candidate for dark matter, because they are surely there. The problem was, I'm still not 100% convinced it should be excluded, but in principle, if you make the theoretical calculation of the integral of how many of those you should have in a galaxy, they don't give you the amount of dark matter that is needed. In any case, so at any point in the galaxy, you will have this mixture. So now I can ask if anyone in the audience would tell me what are the circles, the encircled dot. So the yellow things are the shining stars. These are shining stars. What are these things? Yes. Dead stars. What type? Now look up there. There are three types: white dwarf, neutron stars, or black holes. So first of all, congratulations, for the first part of the answer is correct. Yes. It has to be white dwarf because the other two you don't see. Black holes, you're in no way going to see stellar mass black holes. They also don't ingest matter. Neutron stars, they don't emit light that the HST would see. They emit beam, the radiation, only the moment they spin. White dwarf, instead, are very hot and have that color. So, well done. But the amazing thing is, before this work in '97, that was mostly made by people in Bologna, white dwarfs were only theoretically out of the equation. That should be the end point remnant of intermediate mass stars, but the HST has found the white dwarf cooling sequence, and this is the image I show you. This is just to show you. So this, at least you can see, they are very faint, but you can see it in ultraviolet light because they are very hot. But the other two are only in our integrals. So I'm very happy to show you a paper that we just submitted. So this is very, very new work because up to now, most people, colleagues that do my same, let's say, type of research, we have been busy modeling the light. But now, especially in the era of gravitational waves, it becomes very important to locate remnants. So in this paper, we actually, it sounds a bit creepy, but essentially, we are tracing the graveyards in galaxies. So we not only, with the population modeling, give you the exact age and metallicity distribution of arbitrary galaxies. Here I picked just 4, spanning a range from low mass to high mass. This is the parameter. These are elliptically shaped. These are spirals, again, low mass, high mass. But also, we can tell you where white dwarfs, neutron stars, and black holes are located in your galaxies. It's full of them. It's just a pity that they cannot actually count for the dark matter. So, we are approaching the conclusion. We cannot, in a talk in which I speak about darkness, unless, because that would be very not professional to acknowledge the fact that apart from this type of things that are dark, that we can actually understand, because they are made of normal matter. I would let aside the black holes in this. Well, Professor Vera Rubin in the 60s, I was very happy to meet her back in 2009. Then she passed away. We owe to her the conviction into the community, into the astronomical community, that there is a large amount of dark matter, not only in the early universe to start the formation of galaxies in the first place, but also at the level of galaxies. If you study physics, you certainly have done this at some point, or you will do it. What is the actual probe that this is the case? This is the shining galaxy. And all the remnants that I described will be here, in the middle, where there are stars. But if you move at large distances from the center of light, that you would conclude is also the center of mass, surely the luminous mass, you are expecting that the velocity decrease in a Keplerian fashion as we are used from normal physics. And instead, Vera Rubin calculated all the observed light curves of spirals in the local universe, noting that they are flat. If they are flat, means there must be more matter that sustain the velocity. But that matter is not associated to light because you don't see it. We are deep in the halo of galaxies. And so that's the problem of the dark matter, which is at least 30% of the cosmic pie, which is a bit high. And when I got my PhD in 1998, a colleague from Paris, Jo Silk, told me, don't worry, in a matter of few years, we will find the constituent of the dark matter. And now it's 26 years, and we haven't found it so much that other type of studies entailing abandoning to look for a candidate and instead modifying gravity theory as we know it are taking actually speed because we don't know how to explain this. Okay, so as a very last message, we all would like to rejuvenate, as surely I would rejuvenate. You are young enough, you can stay as you like. The universe is the only place where you can actually at least dream to go back in time. And this is what extragalactic astrophysics, that is what I do, give you the chance of analyzing with this population modeling galaxies back when the universe were younger. So we have created, I'm not selling anything, it's all for free, but I want to tell you, when you have time, go to this website, cosmicstroll.com. We are making apps for both the iPhone and the Android. And inside that, we put the population modeling of all the Sloan galaxy up to I Redshift. We are doing the same for the James Webb data now. Meaning, you can take a stroll in the cosmos and point to real galaxy and see how big they are, how old they are, and how much time in look-back time you are going when you see their light. And hopefully I am on time. I thank you for the attention, and I take questions.